Squeeze theorem and limits involving sine. Some limits are found indirectly by using the squeeze theorem or sandwich theorem. In this approach, we choose two functions that squeeze together at a given point. The given function is sandwiched between these two functions, h of x and g of x. Because the two functions squeeze together at the point, each would have the same limit, concluding that the function between them also has the same limit. The squeeze or sandwich theorem states that if two functions g of x and h of x exist such that g of x is less than or equal to f of x, which is less than or equal to h of x, and the limit of g of x as x approaches c is equal to the limit of h of x as x approaches c, which is equal to L, then the limit of f of x as x approaches c will also equal L. Now the trick is picking the correct functions. Use the squeeze theorem to show that the limit of 4 plus x times the cosine of 1 over x as x approaches 0 is equal to 4. The first step is to reduce the function down to its basic parent function. In our case, it's the cosine of the quantity 1 divided by x. And then the next step to that is to consider the range for this function. All cosine functions with no amplitude change, meaning there's no coefficient in front of cosine, will have a range between -1 and +1. Now, if you had a coefficient of, say, 2 in front of this x, then your a values would be between 2 and -2. Now let's set up what we know about our cosine of 1 over x function for x values that are greater than 0. We know that cosine of 1 over x is between -1 and +1. Also a note, the same proof that we're going through right now is also true for x values that are less than or equal to 0, with a remainder that the inequality sign would reverse when multiplying by x, and you'll see that on the next slide. So to make our cosine of 1 over x resemble what's in the example, which was 4 plus x times cosine of 1 over x, we're going to first multiply all three sections by x. And when we do that, we will have negative x, which is less than or equal to x times the cosine of 1 over x, which is less than or equal to x. And then, to get it appearing as 4 plus x cosine of 1 over x, we need to add 4 within each section of our compound inequality. So when we do that, we have a 4 and then the minus x. We have 4 plus x cosine of 1 over x, and we have 4 plus x. And remember, whatever operation you perform in the center of a compound inequality, you must do to each side. And now what we have is we have two sides of our function. So if we're taking the limit of 4 plus x times the cosine of 1 over x from the left, as x is approaching 0 from the left, we can substitute the x value of 0 directly in for x from this left side of our compound inequality. And when we substitute 0 in there, we get 4 minus 0, which is equal to 4. We can also do the same thing with the right-hand side. We have a 4 plus x. So if we are taking the limit, or finding the limit, as x approaches 0 from the right of 4 plus x cosine of 1 over x, we can use direct substitution with our expression to the right here, 4 plus x. And if we substitute 0 directly in there, we get 4 plus 0, which is equal to 4. Therefore, we can conclude by the squeeze theorem that the limit of 4 plus x cosine of 1 over x as x approaches 0 is indeed equal to 4. Most of the time, substitution will work to find the limit of a trigonometric function. But there are 3 limits that leave you with an indeterminate form. So we will need to know these from memory. The first one is the limit of sine of ax divided by a times x as x approaches 0 is equal to 1. The second one is the limit of cosine of x minus 1 all divided by x as x approaches 0, and that is equal to 0. And the third one is the limit of tangent of a times x divided by a times x as x approaches 0 is equal to 1. We're going to go over this first limit in this topic, and then the other 2 will be discussed in the next one. The first trigonometric limit to know is the limit of sine of a times x divided by the product of a and x as x approaches 0 is equal to 1. The best way to show this limit and what it is to do it graphically with f of x is equal to sine of x divided by x. Notice when we graph sine of x divided by x, the utility won't tell us everything we need to know. For example, if we substitute 0 in, the sine of 0 is 0 over 0. So that doesn't exist here, and the graphing utility doesn't show us that. We know algebraically that a hole exists at x equals 0, despite not being visible in the graph. Because again, when you use direct substitution, you get the sine of 0, which is 0, divided by 0. You get a 0 over 0 indeterminate form. Notice how as x approaches 0 from both sides, from the left and from the right, the function approaches a value of 1, despite being undefined at this point, 0, 1. Therefore, the limit of sine of x divided by x as x approaches 0 is equal to 1. We can use the limit of sine of x divided by x as x approaches 0 is equal to 1 and the scalar multiple property we learned about earlier in the unit to apply it to a general form where a is a constant to say that the limit of sine of a times x divided by the product of a and x as x approaches 0 is equal to 1. Now, not all problems will be as simple as this. Some will require using trigonometric identities to simplify first. Let's actually try a few to see what they look like. Let's evaluate the limit. The limit of sine of 4x divided by 4x is equal to what value? Well, this is almost identical to the limit of sine of ax divided by ax as x approaches 0, and that is equal to 1. So therefore, the limit of sine 4x divided by 4x as x approaches 0 is equal to 1. And this slide shows us the answer, and indeed it is what we found when we worked this problem out. Because the coefficient of the denominator, right here 4 in front of this x, is the same as the coefficient that shows up in the sine function, we can directly apply the limit rule for sine of a times x divided by a times x and have it be equal to 1. Let's try evaluating this limit, the limit of sine of 4x divided by 2x as x approaches 0. Notice that the coefficient in the denominator is not the same as the coefficient in front of the x value in the angle that we're taking the sine of. There's a 2x here, and there's a 4x in the numerator. So in order to evaluate this, we have to get the denominator 2x be equal to 4x. And we can do that by multiplying both the top and bottom by positive 2, because 2 over 2 is equal to 1, and 1 times any number or expression doesn't change its value. So if we multiply by 2 over 2, so that we get 4x in the denominator, then we can take that limit. Then if we simplify the denominator, we have 2 times 2x, which is equal to 4x. Now we have the coefficient in the denominator being equal to the coefficient in the angle. So we have a 4x over 4x. So we can use this formula to simplify for the next and last step. So we can pull out the coefficient of 2 and put it in front of the limit, and we now have 2 times the limit of sine of 4x divided by 4x, and we know that the sine of a times x divided by a times x is equal to 1, so that we can substitute a 1 in place of this limit. So we have 2 times 1, which is equal to 2. Now let's try to evaluate this limit. The limit of sine of 5x divided by the sine of 3x as x approaches 0 is equal to what? This one's a little bit more complicated than what we've been dealing with. So let's take a look at it. This one is a bit trickier because there is a sine function in both the numerator and denominator. For this to obtain the general form that we're looking for, we need to create it in both the numerator and the denominator separately. We can start by dividing the top and bottom, or the numerator and denominator, both by x. When we do that, we will get the sine of 5x divided by x over the sine of 3x divided by x. Then we can multiply the numerator by 5 over 5, which equals 1 and doesn't change its value, and the denominator by 3 over 3. Again, it equals 1, so it doesn't change the value. Then we can simplify it further using the properties of limits. We can take the coefficient of 5 from the numerator outside of this limit, and then we have 5 times the limit of sine 5x divided by 5x as x approaches 0, and we can do the same with this 3 coefficient that's in the numerator. We can pull it out, and now we have the limit of the sine of 3x divided by 3x as x approaches 0. Then we can simplify using the general form of the limit of sine of a times x divided by a times x as x approaches 0 is equal to 1. So because we have the limit of sine of 5x divided by 5x as x approaches 0, and the limit of sine of 3x divided by 3x as x approaches 0, we can substitute 1 in for both of those. So now we have 5 times 1 divided by 3 times 1, which is equal to 5/3.